Welcome to today's presentation entitled Introduction to the Theory and Application of Quaternions. My name is Dr. Jim Beatty, and I work at the NASA Langley Research Center in Hampton, Virginia. I'm a member of the NASA Engineering and Safety Center's Flight Mechanics Technical Discipline team. This presentation is part one of a two-part discussion about Quaternions and is sponsored by the NESC as part of its educational outreach program called the NESC Academy Online, which is a collection of video and audio presentations in a number of technical disciplines of interest to the NASA community. The overview on page 2 discusses what's going to be covered in today's presentation, part 1, the Introduction to Quaternions, as well as what will be covered in part 2, entitled Working with Quaternions. In today's presentation, we'll cover the definition, mathematical prerequisites, and properties that Quaternions obey. We'll also compare them with Euler angles and direction cosine matrices that are typically used in flight mechanics applications. Well, what are Quaternions? Quaternions are mathematical abstractions. That in itself doesn't say very much, as you might recall from your first classes in mechanics, where you, or even mathematics, where you were given descriptions of vectors, and kind of the same abstractions are used for vectors. What are vectors? They are mathematical abstractions used to represent things, and so Quaternions are kind of that vague and unfamiliar when you're first using them, but hopefully after today's presentation and that of part 2, you'll become more familiar with Quaternions and how they actually are used and what the utility they are for doing very useful things. Quaternions were originally invented, or discovered if you will, by several mathematicians in the 19th century, pretty much about the same time, independently. And notably, one of the ones whose name is often associated with Quaternions is Sir William R. Hamilton, a famous British mathematician who had many contributions in mathematics and engineering. In math terms, a quaternion is a type of tensor. In simple terms, a tensor can be categorized as one of the following. You could have a rank 0 tensor is nothing more than a scalar, and that means that it's invariant with respect to any particular reference frame. A rank 1 tensor is a vector, and it is dependent on a particular reference frame. It can be transformed from one frame to another, and the size of the vector, that is the number of elements that it contains, is dependent on the application. Given that we normally deal with flight mechanics applications in three-dimensional space, typically the vectors that we refer to are three-element vectors, such as position, velocity, acceleration of an object relative to some reference frame. But mathematically, vectors are not limited to 3 elements, just in the application that we typically use. A rank 2 tensor can be represented as a matrix, and it often is in the types of analyses that we do. Rank 2 tensors, such as a linear transformation or a direction cosine matrix, is a rank 2 tensor. A moment of inertia tensor of an object is also a rank 2 tensor. And again, the size of the matrix, which is the number of rows and number of columns, is dependent on the application. But again, since we deal typically in three-dimensional space and three-dimensional degrees of freedom, rotationally that is, most of the rank 2 tensors that we would use in flight mechanics applications are 2x2 matrices, or can be represented in that form. A tensor also can either be covariant or contravariant, depending on what type of transformation law it obeys. Most of the vectors that we use, or tensors that we use in flight mechanics, are contravariant, meaning they vary contra, or opposite, to how the basis vectors vary. For example, if you have a vector, some fixed vector in space that is represented in some coordinate frame with some components, call them x, y, and z, as you rotate that frame, if the vector is fixed, the components of that frame vary, obviously. That's one of the reasons we use vectors to describe motion. And if you look at them carefully, if you rotate a frame, it appears that the components of that vector kind of vary opposite to the direction that the frame is rotating, and that's what contravariant refers to. So we won't get into that today. That's a whole other subject of tensor analysis, but just as a way of defining or summarizing what tensors actually represent. How do quaternions compare with vectors? Well, like vectors, quaternions are ordered groups of real numbers. That's, you may remember, one of the definitions they give you of a vector when you first start studying mathematics. And then, although some people actually can represent quaternion operations with complex notation, and there are some applications where the quaternions are complex, and again, in the flight mechanics applications that we'll talk about primarily today, they are real ordered groups of real numbers, typically written as a row or column vector. Quaternions also have mathematical properties, much like vectors, with respect to some operations, and those properties and those operations can have commutative or associative or distributive properties. Quaternions also can be added, subtracted, multiplied, divided, even more. We won't cover them too much today, but you can actually take logs of quaternions and take exponentials of quaternions, and there's lots more you can do with them. But unlike vectors, quaternions have 4 elements instead of 3. And as the subnote here says, actually vectors, again, are not limited to 3 elements. But in the dynamics and kinematics applications that we typically use, we normally think of vectors as 3 elements because we're representing 3-dimensional motion. And again, so quaternions then would have 4 elements instead of the 3 that we normally would work with position, velocity, acceleration vectors. How are quaternions represented? Usually quaternions are represented as a 3-element vector and a scalar part. So for instance, the quaternion Q that I'm showing here on this slide can be represented as a scalar part S and a vector part V. And notation-wise, it can be shown as indicated there, just a scalar and a vector kind of in brackets or parentheses or whatever. Or it can be represented as an algebraic expression, as a scalar S plus a component X times the basis vector I plus a component Y times the basis vector J plus a component Z times the basis vector K, where I, J, and K are the basis vectors of some reference frame, and obviously X, Y, and Z are the components of the vector V in that frame. Or you could write the quaternion in kind of a quaternion subscript notation as a scalar part Q0 and vector parts Q1, Q2, and Q3. And again, as I mentioned earlier, those can be implemented as a row or column vector of 4 elements for manipulation purposes. The scalar part can represent time, a rotation angle, or virtually anything else, depending on the application. In kinematics use, the scalar part is usually related to a right-hand rule rotation angle about the direction that's specified by the vector part. In mechanics use, meaning something like Einstein's theory of relativity or such, the scalar can be related to time, and the vector part would represent position, velocity, or acceleration. So then the 4 elements, or the 4 dimensions of that quaternion, represent the 4 dimensions of space and time. And reportedly, Einstein actually used quaternions in his development of the theory of relativity. Quaternions have virtually unlimited applications and cover lots of different aspects of things. One of the more common applications nowadays that are used is for virtual reality and video games, where you're attempting to envision a scene as the person or the visual aspect of the scene is moving around. So if you're moving through a scene of a video game, you want to represent how the scene would change to make it more realistic. And so they can be used there for very rapid and efficient rotation of scenes in a virtual video game or virtual reality type application. In this presentation, however, we will concentrate on the kinematics use of quaternions for things that we would normally use in flight mechanics arenas, such as coordinate transformations or describing the orientation of one frame relative to another, or an object relative to some frame, etc. And again, how are specifically quaternions used in kinematics? As shown in the top bullet there on this slide, the quaternion Q is represented as a scalar part theta and a vector V. And theta in this notation would be the rotation of some object or reference frame as a right-hand rule rotation about this vector specified by V. As shown in the diagram on the right, you see a vector V relative to some coordinate frame with axes X, Y, and Z, and you also see a unit vector along the direction of V, and then you see the angle theta, which is depicted as a right-hand rule rotation about that vector v. A more common way that you would express quaternions in flight mechanics applications, however, instead of a scalar part theta and a vector v, would be a scalar part which is cosine of the angle divided by 2, and a vector part which is sine of the angle over 2 times n, where n is a unit vector along the direction of the velocity, or excuse me, the vector v. So, for instance, n is just vector v divided by its magnitude. The latter form, as shown there, where q is cosine theta plus n sine theta over 2, is convenient because it's a unit quaternion, which we'll get into a little bit more, meaning its magnitude is 1, which means the sum of the squares of all the components, the scalar and the 3 vector parts, equals 1. And that will simplify some of the mathematics to follow. Also in this latter form, the elements of the quaternion are what's known as Euler parameters. And you'll see that term in some textbooks and technical papers. You might also see something referred to as Euler-Rodriguez parameters, which are similar to Euler parameters or quaternions as presented here, but they've used the fact that in this form, as described, the quaternions are unit quaternions. As I said, what that means is the sum of the squares of the scalar part and the vector components equals 1. Well, that relationship can be used to replace one of those 4 things with a combination of the others. And what's typically done for Euler-Rodriguez parameters is the scalar part is represented as 1 minus the sum of the squares of the vector parts and can be eliminated. There is some risk in doing that, though. You give up something in that in that form, we won't go into Euler-Rodriguez parameters here, but in that form, you can introduce some singularities that can occur for certain orientations of reference frames. And one of the points of using quaternions is to avoid ambiguities in defining a frame. So that's one of the things you give up with Euler-Rodriguez parameters in the desire to simplify them to 3 independent parameters instead of 4 parameters with a constraint equation involved in them. Quaternions can be used to add and subtract, and they have certain properties, much like scalars and vectors do. If you have 2 quaternions, Q1 and Q2, where each has a scalar part S1 and S2, and each has a vector part V1 and V2, then the sum of the 2 quaternions is nothing more than the sum of the scalar parts, and the vector part of the sum is the sum of the 2 vector parts. The difference, conversely, is just nothing more than the difference in the 2 scalar parts and the difference in the 2 vector parts. And you'll note, if you look into the literature, you'll find that some people define subtraction using a scale factor, as shown here, where Q1 minus Q2 is the difference in the scalar part combined with the difference in the vector part divided by 3. And you wonder, why is that factor of 3 there? And those texts described as this form preserves some of the holonomic characteristics of quaternions. We won't get into that here because typically in the types of applications that we use, you will not find such scale factors. It's just as shown in the top part of the slide. Quaternion addition is associative and commutative, where subtraction is associative but not commutative, as we all know. It's just like subtracting and adding vectors or scalar components. It's associative in that if you add or subtract 3 quaternions, you can add the first one to the sum or difference of the second 2, or you can sum and difference the second 2 and add them to the third. And it makes no difference in the answers. And if it's just 2, you can say Q1 plus Q2 is Q2 plus Q1, but as you might imagine from your experience with scalars, Q1 minus Q2 is not the same as Q2 minus Q1. In addition, there's, as I mentioned, quaternions can be multiplied, so they obey certain mathematical relationships of multiplication, just like scalars do. Quaternion multiplication is associative, but it's not commutative. In other words, it is order dependent. So again, if you have multiplication of 3 quaternions, you can multiply the first one times the product of the second and third, or you can multiply the product of the first and second times the third, and it makes no difference on the final result. However, Q1 times Q2 is not equal to Q2 times Q1. Now, again, if we have 2 quaternions, Q1 and Q2, each of which has a scalar part S1 and S2, and a vector part V1 and V2, then the product of Q1 and Q2 can be expressed as shown there, where the scalar part of the product is the product of the two scalar parts of the two quaternions minus the dot product of the vector part of those two quaternions. Then the vector part of the product is the product of the scalar part of quaternion 1 times the vector part of quaternion 2 plus the scalar part of quaternion 2 times the vector part of quaternion 1 plus the cross product of the two vector parts. And we'll present some other forms later that make it a little bit easier to do these calculations. That primarily can be written as a a matrix vector product, which makes the manipulations a little bit easier. One interesting fact to note, if you look at that form, though, is if you were to multiply two quaternions with a zero scalar part, now there's just two pure vectors, that would produce a quaternion with the negative dot product of the two vectors as its scalar and the cross product of the two vectors as its vector part. And Hamilton reportedly used this fact to implement dot and cross products before the concepts were invented in modern vector algebra. So he was a very intuitive person mathematically, as we all know. Other properties of quaternions. Quaternions can have a conjugate, which is similar to the concept of a conjugate of complex numbers. As you might recall from complex numbers, if you have a complex number that's a real part plus an imaginary part times I, where I is the square root of minus 1, then the conjugate of that number is the real part minus the imaginary part. And conversely, or similarly, quaternions have a similar type definition of the conjugate. If Q represents a quaternion with a scalar part S and a vector part V, then its conjugate is S as a scalar part and minus V as its vector part. And obviously, the conjugate of a quaternion would return back to the original quaternion. And the quaternion has a magnitude, or what's also called the norm. Again, if Q is a quaternion represented by a scalar part and a vector part, where the vector part is represented as components x, y, and z relative to the basis vectors I, j, and k of some reference frame, then the norm of Q is the square root of the sum of the scalar part squared and the individual components x, y, and z squared. Quaternion has an inverse as well as a conjugate, and how are they related? The product of the quaternion and its conjugate can be written as shown here. If Q star represents the conjugate of the quaternion as defined on the previous page, then the product of Q and Q star, going back to the form that was shown several slides ago, you can show that it results in a quaternion with zero vector part and the scalar part as the sum of the squares of the elements of the quaternion. And that we described or showed on the previous slide that sum of the square of the components is the norm squared of the quaternion. So from that relationship shown above, it's real easy to show that Q times its conjugate Q star divided by the norm squared equals 1, or putting those in a different form, you could say the inverse must be the conjugate of the quaternion divided by its norm squared, and that's exactly how the conjugate of a quaternion is defined. I mentioned earlier, you might recall, that in the form that we typically write quaternions for flight mechanics applications, it's defined as a unit quaternion, which means nothing more than the norm is equal to 1, or the sum of the squares of the four elements of the quaternion is equal to 1. And if you look at that in the expression above, then for the inverse of a quaternion, if the norm is 1, then the inverse is nothing more than the inverse of the conjugate is nothing more than its conjugate, which will be very useful in doing some of the manipulations that you will do in flight mechanics application, in that you can very simply compute the conjugate without having to divide by the RSS, or the root sum square of the components of the quaternion. You can also multiply a scalar by a quaternion by a scalar. And the form that's shown here is if Q is a quaternion, again with a scalar part S and a vector part V, then some scalar K times that quaternion can be represented as another quaternion with a scalar part Ks and a vector part Kv for any real scalar K that you want to pick. And you can show that real simply by going back to the definition of the product of two quaternions and have one of the quaternions have a zero scalar part. And you do the calculation that we described earlier that shows the combination of the dot and cross products of the elements of the vector parts, and you'll see that you get the relationship shown there. Now, what would you get if you multiplied a quaternion by -1? And so for the purposes of this discussion, I'll define a special quaternion. We'll call it QM1, as defined as a quaternion with a scalar part of -1 and a vector part of 0. And you can write that as, -1 and 0 times n, where n is any vector you want to pick. It really doesn't matter because you multiply it by 0. But we'll leave it in there for the purposes of this discussion. So also notice that that quaternion with a vector part of 0 and a scalar part of -1 can also be written in the standard form that we described earlier in the form of scalar part of cosine of some angle theta over 2 and a vector part of sine of that angle divided by 2 times some vector n, where in this instance, for this particular special quaternion, theta is plus or minus 2 pi n, where n is any odd integer, 1, 3, 5, etc. So then we can rewrite that quaternion as cosine pi plus or minus pi n and n times sine plus or minus pi n, and you see that's nothing more than -1 as a scalar part and 0 as a vector part for any odd integer n. So the multiplication of any quaternion by -1 gives the same quaternion just rotated by plus or minus 2 pi n. So the orientation of that quaternion, or the orientation of the frame or of object defined by that quaternion, doesn't change when you multiply it by -1. And quite often people will use that fact to adjust a quaternion calculation after the fact if the scalar element is -1. Just as a matter of course, a lot of times in applications you will see, if some equation is calculating a quaternion from some relationship that we'll describe later in this presentation, also in part 2, one of the first things you do after you compute the quaternion is you look at the scalar part, and if it's a negative number, you would negate the entire quaternion, all 4 elements of the quaternion. And that has no effect on the ensuing validity of that quaternion or the orientation defined by that quaternion. Now we'll discuss another method that you can use to multiply 2 quaternions. If we have 2 quaternions, Q1 and Q2, where again the scalar part of quaternion Q1 is called S1, the vector part is called V1, and the scalar part of quaternion 2 is called S2, the vector part is called V2. Recall from an earlier slide that the product of Q1 and Q2 can be computed as shown here as a function of multiplications of the scalar parts with the vector parts and dot product of the vector parts, cross products of the vector part. It can also be computed as what I'll call manually as follows, by defining first the product of the basis vectors I, J, and K as shown here. The first collection shows that I times J produces K, J times K produces I, K times I produces J. And those are order dependent. So in the reversed order, Ji would produce minus K, Kj would produce minus I, and Ik would produce minus J. And these are similar to the cross product type characteristics you would have between those basis vectors, where for instance I cross J is K, and J cross K is I, and K cross I is J. And then again with cross products, the reverse of those, they're order dependent. So then J cross I would be minus K, and K cross J would be minus I, and I cross K would be minus J. So that part of just the straight product of the basis vectors as used in quaternions is very similar to the kind of situations you have with cross products of those same basis vectors. Now also there's another thing that's a little different than the way you get when you're crossing basis vectors. You'll notice terms like I times I, now for the use in these quaternions, is going to be minus 1, and J times J will be minus 1, and K times K will be minus 1. Whereas in the cross product world of looking at the basis vectors, and of course I cross I would be 0, and J cross J would be 0, and K cross K would be 0 for cross products, because those terms are parallel, and since they're the same vector, and the cross product then would return 0. But in this case, for the quaternion use, those products of the same basis vector with themselves just produces minus 1. And again, note those multiplications are not commutative. They are order dependent. So now, having made use of those terms, we can compute that product Q1, Q2, just as I call it, term by term. So if Q1 is just defined as an algebraic sequence, S1 plus X1I plus Y1J plus Z1K, where again I, J, and K are the basis vectors of which the vector part of Q1 is defined, and then quaternion 2 is defined as the algebraic collection of S2 plus X2I plus Y2J plus Z2K, then those two algebraic expressions can just be multiplied term by term, taking care now not to swap the order of the multiplications. When you do that, you'll get just a collection of scalars, parts, and vector parts multiplied by each other, some without any basis vector contributions, and some with I or J or K. And so the parts that don't have I or J or K in them are just the total scalar part of that vector, that quaternion product. And then so the approach would be you just collect up all the scalar parts, all the parts that are proportional to the basis vector I, all the parts that are multiplied by the basis vector J, and all the parts that are multiplied by the basis vector K. And that's what we'll continue on the next slide to present this in a form that is actually normally used. Normally when you've written it out like this, you can just you might have a function or something like a MATLAB function that does quaternion multiplication that would go ahead and show it as shown on the next page, or you might do as what's going to be shown later, 2 slides from now, as a matrix vector product. So again, if we group the previous expression for the term-by-term multiplication of the two quaternions, you'll see we'll get basically 4 parts of that, where the first part is a S1 times S2 minus X1 times X2 minus Y1 times Y2 minus Z1 times Z2, etc. And you get a similar term like that for each of the vector parts. Then that's nothing more than another quaternion with a scalar part S and the vector parts X, Y, and Z, where S, the scalar part of the product of the two quaternions, is as shown there, and the vector parts X, Y, and Z of the product of the two quaternions is also as shown there. And we'll complete that a little bit more on the next slide by writing that as a matrix equation. So if you just rearrange the equations on the previous page for that multiplication, then you can express it as one of 2 different types of, and 2 equivalent types of matrix vector products. You can either write Q1 times Q2 as capital Q1 times Q2, or capital Q2 times Q1, where capital Q1 and capital Q2 are just 4x4 matrices. And they have similar characteristics, as we'll describe in a moment. Q1, the form shown on the left of the equation above, is referred to in the literature as the quaternion matrix. Capital Q2, the 4x4 matrix shown on the right side of the equation above, is referred as the quaternion transmuted matrix. And you'll see those terms quite often in the literature, so just keep in mind which form those are. And note they also have some similarities in their form. Both of those 4x4 matrices are skew symmetric, and they have the following properties. The scalar part of the quaternion runs down the diagonal of each of those matrices. The quaternion itself is in the first column of the matrix. The conjugate of the quaternion is in the first row of the matrix. And then the off-diagonal elements of the lower 3x3 matrix within the larger 4x4 matrix are skew symmetric, as I mentioned earlier, and they also have similar characteristics, but they're reverse polarity from each other. And what you'll notice if you look at the one on the left, the area shaded on the left, capital Q1 matrix, the form of that is very similar to the form you might have seen for performing a cross product or implementing a cross product of a vector by way of a 3x3 matrix. You might remember that form. The 3x3 part of the cross product of a vector is zeros down its diagonal, and then the minus x component as the 2,3 element, the y component as the 1,3 element, and the minus z component as the 1,2 element, etc. So the quaternion matrix itself, the Q matrix on the left, that lower 3x3 is very similar to how you would implement a cross product. So that can be a little memory jogger if you're trying to remember the form of that equation and which polarity goes with which element. The one on the right, again, is just a similar thing, but you're using the second quaternion, Q2, to populate the 4x4 matrix. I'll talk a little bit about the definition of the scalar part, because there are some conventions that different people do a little differently that it's probably one of the more common sources of confusion in working with quaternions. And where is the scalar part in the form or in the method that the quaternion is used is represented in? The quaternion elements we showed on the previous page define or assume a certain definition of the quaternion. If Q, the quaternion Q, is represented as a scalar component called Q0 and vector components Q1, Q2, and Q3 that are part of the multiplied by the basis vectors ij and k to create the vector part of the quaternion, then you can write that as a 4-element column vector with the first element Q0 as the scalar part, and then the next 3 elements Q1, Q2, and Q3 as the vector part. But occasionally some people do two things slightly different in their implementation or their representation of the quaternions as a 4-element vector. Some people don't like the subscript 0 as for Q0. They prefer the elements, instead of being Q0 through Q3, they would prefer they be Q1 through Q4. And some of that gets back to just some of the limitations on certain programming languages that don't allow indices and arrays to have a value of 0. Some, like Fortran, generally do not. Some flavors of Fortran do. Others, like C, can accept and normally expect the first element of an array to be index 0. So anyway, some people define them just for consistency with those restrictions, if you will, or those conventions. So for instance, let's say there's an alternate representation of that same quaternion Q as Q1, Q2, and Q3 as the vector parts, where Q1, Q2, and Q3 are the components of the vector relative to the basis vectors ij and k, and Q4 now is the scalar part. And if that is represented as a 4-element column vector, Q1 through Q4, then obviously the form shown on the previous page for how to use a matrix vector multiplication to do quaternion multiplication will not be correct, because the form of that equation and the elements of the 4x4 matrix were dependent on the quaternion being written in the form shown at the top of this page, where it's Q0 through Q3, where Q0 represents the scalar part, and Q1 through Q3 represents the vector part. So the message here is just be very careful when you're reviewing literature, or if you're working with someone who has a different definition of quaternions than you might be expecting. You can expect trouble there. The next couple of slides, I'll get into a little brief summary of Euler angles and direction cosine matrices, which are very closely related to quaternions from the standpoint of how we might use them in a flight mechanics application. So I want to do a little short, brief review of Euler angles and direction cosine matrices that we will build on in part 2 of the quaternion presentation. Euler angles define the orientation of one frame relative to another that can be specified by 3 sequential rotations about x, y, and or z axes in any convenient sequence that is dictated by the application or user's preference. You might remember Euler's theorem that says any reference frame can be rotated to align with any other reference frame using just 3 rotations. So that's kind of the basis of Euler angles as we normally use them in the flight mechanics application. And Euler angles, to a lot of folks, provide a very intuitive representation of the relative orientation of those 2 frames. You can visualize them very easily. You might think back to the frame that we typically use in aerospace applications quite often to define the orientation of an aircraft or spacecraft or missile or rocket relative to, say, some Earth-based frame as a yaw, pitch, roll sequence, where you yaw it first through an angle typically called psi, you pitch it about the y-axis through an angle called theta, and then you roll it about the x-axis through some angle called phi. And those, if you have used those type constructs a lot, you kind of can visualize it. You understand what roll, pitch, and yaw means. You can visualize how the object would be oriented in space, and it's very intuitive. But one of the things with Euler angles, you can't really directly transform vectors using Euler angles themselves. I mean, you can, but typically it's not done that way. typically what you would do is you'd first take those Euler angles and use them to create some direction cosine matrix or some other transformation method first, and then you'd use that DCM or that transformation matrix to actually do vector transformations. And also, it's rarely used, and I'll say rarely, some people still do it, but you can also integrate the angular rates of the Euler angles to simulate the vehicle angular motion, and I'll describe that on the next chart here. There's a couple of benefits to that and disadvantages. The benefit is that such a process only requires 3 states to be integrated. That is the 3 Euler angle rates. Again, going back to our yaw, pitch, roll sequence that we described earlier, you can write an equation for phi dot, theta dot, psi dot, integrate those, and you get phi theta psi, so it only takes 3 integrations to keep track of the state changes. But usually you'll find a couple of disadvantages to integrating Euler angle rates for use in a simulation or an inertial navigator or whatever the application is, that usually it would require a smaller step size in your numerical integration than propagating DCMs or Quaternions. And the reason is that you'll see in the next slide is the rate of change of the Euler angles is generally larger than that of the DCM or Quaternion elements, meaning you have to make your step size smaller to accurately integrate that numerically. And also, the biggest disadvantage of trying to integrate Euler angle rates is some orientations, when they're coupled with a specific Euler angle sequence, can result in singularities of the Euler angle rates, as we'll see in the next slide. As promised, here's a slide talking about time propagation of Euler angles. So again, going back to our traditional aerospace sequence of yaw, pitch, roll Euler angles, which define the reference frame of usually the body frame of some object relative to a reference frame, either based inertially or based on the Earth or some convenient frame. You will find that if you write out the equations for what phi dot, theta dot, and psi dot are, which are the 3 Euler angles in a yaw, pitch, roll sequence, then you'd see the equation shown here, where phi dot, theta dot, psi dot as a vector equals a matrix, 3 by 3 matrix times P, Q, and R, where in this notation P, Q, and R are the are the angular rates of that second frame relative to the initial frame, and they are measured in that second frame. So for a vehicle, for instance, P, Q, and R would be the angular rates of the vehicle relative to that first reference frame, with P, Q, and R measured in the body frame that's rotating. And what you'll see is the first thing I mentioned earlier on the previous slide about typically, or in general, Euler angles requiring a smaller step size. You'll see one of the reasons why. The first equation there for the roll angle Euler angle rate, phi dot, is directly proportional to P. You'll see the 1 and element 1, 1 of that matrix. So phi dot is directly proportional to P. So basically, it basically changes faster than you'll see later with Quaternions or direction cosine elements, which are proportional to something less than 1 times the angular rates. So in general, that takes a larger step size to accurately perform the numerical integration of phi dot, theta dot, and psi dot. However, the biggest disadvantage you'll see here is if you look at those equations carefully, you'll see that the first equation for phi dot is proportional to tangent theta for the latter 2 components, and the third equation is proportional to 1 over cosine theta. And obviously both of those have an issue if cosine theta is 0, and that would occur for theta, this intermediate Euler angle, at a value of plus or minus 90 degrees, because then tangent theta would go to 0 at 90 degrees, and cosine theta would go to 0, and the expression for phi dot and psi dot would be indefinite, in other words, divided by 0. So there is a singularity in the Euler angle rates for that particular orientation when the intermediate angle is plus or minus 90 degrees. And that's one of the biggest disadvantages of trying to integrate or do time propagation of the Euler angles and then integrate them to get the changes in the Euler angles themselves. You can avoid that by doing this using direction cosine matrices or Quaternions to define those orientations, as we'll see on the next slide. Again, just a brief review of direction cosine matrices and how they're similar to Euler angles, but yet different. And we'll see in the next part 2 of this presentation how DCMs and Euler angles are similar to Quaternions, but slightly different also. But a direction cosine matrix, or DCM, provides the methods for transforming vectors from one reference frame to another, usually implemented as a matrix multiplication operation. So a 3 by 3 matrix times a 3 by 1 column vector equals another 3 by 1 column vector, which happens to represent the transformed components of some vector. The rows of a DCM are nothing more than the direction cosines of the rotated frame axes, x, y, and z, relative to the original frame. And again, they represent the transformation, as shown here, from the reference frame depicted by capital XYZ to the rotated frame depicted by XR, YR, and ZR. And again, in the notation shown above, the lowercase ij and k are the basis vectors in the rotated frame, and the uppercase ij and k are the basis vectors of the reference frame. The DCM, one of the characteristics of DCMs is it's orthogonal, meaning the inverse of the DCM equals its transpose, and then each row and each column has a root sum square value of 1. In other words, if you take the sum of the squares of any row or column in the DCM, it equals 1. That fact can actually be used to reduce the number of states that have to be propagated. So instead of being 9 independent parameters in that 3 by 3 matrix, there's really only 6 of them that are independent. Similar to Euler angles, you can perform time propagation of DCMs. So if you have an initial DCM and some prescribed angular velocity of an object or a frame, as time progresses, then you can calculate the rate of change of the elements of the DCM as shown here. And we'll define, or I'll actually describe how you come up with the equation for calculating the rate of change of C dot. Since the DCM is orthogonal, its magnitude is invariant. So if you take the time derivative of that 3 by 3 matrix, or that rank 2 tensor, if you will, it's equal to 0 because it is invariant. And then also remember the rule for performing time derivatives in a rotating frame, then d by dt of the DCM represented by C there is nothing more than C dot plus omega cross C, where C dot is the rate of change in the local or rotating frame. Or rearranging that, then C dot is minus omega cross C. Then you can write that out as C dot is minus PQR crossed with C. So basically you have a 3-element row vector PQ and R crossed by a 3 by 3 matrix. And so it's a very simple expression to calculate. This implementation of time propagation of the DCM allows a larger integration step size than integrating Euler angle rates, because as you'll see, the elements of C, the DCMC, are all less than 1. As I described earlier, the RSS value of any row or column of C is 1, so each individual element is less than or equal to 1. So that you can see very clearly then the product C dot, each element of C dot is basically the angular rates PQ and R multiplied by something smaller than 1. So in general, you can get by with larger integration step size when you perform numerical integration of the time rate of change of the DCM, as opposed to doing the same process with the elements of the Euler angle rates. And this integration process would require then 9 state equations, one for each of the elements of the 3 by 3 matrix. But again, if you actually use the row column orthogonality constraints that were described earlier, you can reduce that to 6 integrations. And typically, again, just as a matter of summarizing or reviewing DCMs, typically though DCMs represent multiple sequential axis rotation. As I described earlier, with Euler angles, you define a rotation about typically 3 individual rotations about different axes, and so the DCMs then can be represented by just chaining simple one-axis DCMs into the proper sequence, as I'll describe here for our traditional yaw pitch roll sequence. But I want you to note here that the order of multiplication of these simple DCMs is very important for comparison with quaternions to follow. So for instance, for a yaw, then pitch, then roll Euler angle sequence, the DCM of that aggregate or combined rotation sequence is as shown there, where on the right side of and keep in mind each of those is a 3 by 3 matrix multiplication. So on the right side of that, that's depicted as C sub psi. That's a yaw angle rotation 3x3 matrix. The second one, second most from the left, C sub theta, is a pitch axis rotation, and C sub phi, the leftmost, is a roll axis, where each of those can be expressed as shown below. And those general forms of rotation about the x-axis, which is what is depicted by C phi, or rotation about the y-axis, which is represented in the center by what's depicted as C sub theta, or z-axis rotations, what's depicted on the right as C sub psi. Those are general, and the order can be mixed and matched for whatever rotation sequence you want to do, and then you just chain together those rotations, but in the proper order as shown in that aggregate equation above. C equals C phi times C theta times C psi. Now, if you continue from that example on the previous page, if you actually algebraically write out those three multiplications of the 3x3 matrices as depicted on the previous page, you get the form shown on the top of the top equation on this slide here. Now, just for comparing it with Euler angles, let's say, for instance, in this implementation, the intermediate angle theta is plus or minus 90. If you actually replace theta in the expression at the top of the page by either plus or minus 90, that DCM would reduce to the form shown in the center of the slide. In other words, it's proportional to plus or minus sine or cosine of phi minus or plus psi. And so what that shows is if the intermediate angle theta happens to be 90 degrees, then that DCM matrix C can only determine phi plus or minus psi. It cannot determine any unique values of phi or psi because there are none. They're basically any combination of phi plus or minus psi is valid. So what I mean by the plus or minus there, to make it a little bit clearer, if theta is plus 90, the DCM can be used to compute only phi minus psi. So you can get a valid, accurate expression for phi minus psi, but you cannot find individual unique values of phi or psi. Any combination of phi and psi that comes out to be the difference phi minus psi computed from that equation is valid. And this illustrates the ambiguity possible with Euler angles. For rotations about three independent axes, if the intermediate or the second rotation is plus or minus 90, the DCM cannot be used to compute unique values of the other two angles. But the DCM itself is still valid, and the rate of change of that DCM, as shown on the previous page, is still finite even at plus or minus 90. So that's one of the huge benefits of using DCMs as opposed to Euler angles for propagating the orientation of a reference frame. But this ambiguity, if you have a DCM and you're trying to back out what the individual Euler angles are, the fact that you can't do it when the intermediate angle is plus or minus 90 is basically the same type of issue that we had with the Euler angles when the orientation is plus or minus 90 for them that we showed a few moments ago. So in summary, this concludes this section of the presentation. In part one, we've covered the following topics: definitions of quaternions, mathematical properties of quaternions, alternate expressions for multiplication using matrix vector forms, which might be easier to manipulate, and a little summary of DCMs and Euler angles that we'll use in part two to kind of clarify how quaternions are similar yet different from DCMs and Euler angles. And in part two of this presentation, entitled Working with Quaternions, we will cover the following: how we actually use quaternions in kinematics, and how we define quaternions for a particular coordinate frame rotation. And in that context, we'll show several examples for typical rotation sequences that we might use. For instance, the roll, pitch, and yaw sequence that we've discussed quite a bit today in this presentation, as well as other frames like north, east, down, or east, north, up, or plumb line frames, or etc. We'll show how you can compute quaternions for each of those, and basically for any arbitrary rotation sequence you want to use. How we use quaternions then for coordinate transformation vectors. We'll cover that, which is one of the main reasons we would want to use quaternions. Then once we have a quaternion, how we can compute the DCM from that and vice versa, so that you can switch back and forth between DCMs and quaternions very readily using the expressions that will be presented. And as we showed here for Euler angles and DCMs, we'll discuss the time propagation of quaternions, an expression for how you compute how it changes with time for a given angular rate of the frame that it's associated with. And then finally we'll use in the second part an expression for how do you use a quaternion to do a single axis rotation that will align one coordinate frame with another. And this latter application is used very often in flight mechanics, in flight software to orient a body relative to some desired orientation. So let's, for instance, you have a rocket that you fly and you want it to fly a certain trajectory with a certain orientation, and at any instant it's got some other orientation. You can define very easily what's called an error quaternion that represents how you get from where you are to where you want to be in a single rotation. And then the elements of those rotations in each of the axes of the vehicle are then feed into the control laws that make it rotate to satisfy or to reach that desired orientation. So this concludes part one of this two-part discussion about quaternions. I hope that you found this presentation to be useful and informative, and I invite you to continue with part two of my presentation. Thank you.